Hello everyone, Dr. Cheng here. So today, let's go over a few examples in one-dimensional motion. So let's first see what we have learned. We have learned the definition of displacement, which is a vector, and it's your final position subtract initial position. That's the definition of displacement. And then we primarily will be interested in the velocity. And by definition, velocity is displacement over time. Displacement over time give you velocity. And then we have acceleration, which is change of velocity over time. And we have studied a special case of motion, which is motion with constant acceleration. Of course, we also learned constant velocity motion, and we said for constant velocity motion that basically is one kinematic equation. Your velocity is a constant, so your displacement is just the velocity times time. And then for motion with constant acceleration, we have summarized the three kinematic equations that we're going to use. First of all, final velocity equals initial velocity plus acceleration times time. Second, displacement equals initial velocity times time plus 1/2 at squared. And then we have a third one. Sometimes it's convenient for us to solve the problem using the third one. And how should we solve the problem? So usually we need to draw a picture to see how the problem works, and then write down all the known quantities, and then write down what quantities the problem is asking for, and then go back to those three equations and see which one has these three known quantity and one unknown quantity. And you can see these three equations, all of them have four variables, right? So if you know three of them, you can solve the fourth one, which is unknown. And then the fourth step, the last step is just your algebra. How good is your algebra? And for our class, let's emphasize on the physics, how to interpret the physics. So let's see the first example, Daytona 500. We have a race car starting from rest. Which gives us the initial velocity 0 meter per second, right? Accelerate at a constant rate, so it's constant acceleration motion. Accelerate at a constant rate, 5 meter per second squared. It tells it should be a constant acceleration motion, so we need to use one of those three equations to solve the problem. And it asks us three quantities. So let's solve them one by one. The first question, what's the velocity of the car after it travels 100 feet? And what should we do here? I think first we need to convert everything to SI unit, right? So we need to convert 100 feet to meter. And how to do that? We multiply by ones, if you can still recall. We want to get rid of feet. So feet should be here. And we would keep meter. We would just write 1 meter here. So how many feet do you have in 1 meter? We have 3.28 feet in 1 meter. So 1 meter over 3.28 feet give you 1. So you multiply 100 feet by 1. This is exactly 1, and you see it will unit cancels 2. So now we can do the calculation. Now we can cancel feet and feet, give us a few numbers to calculate. 100 over 328 meter, and that gave us 30.5 meters. So 100 feet is 30.5. So that's what we know. So we know displacement is 30.5 meter. We know initial velocity is 0. And we know acceleration is 5 meter per second square. We do know three quantities. Do you see that now? We have initial velocity, we have acceleration, we have displacement. And we want to find out what is final velocity. So what is Vf? Which equation should we use to solve this problem? You have to find out the equation that has initial velocity, has displacement, has acceleration, and ask you for final velocity. So we know initial velocity, we know displacement, we know acceleration, we solve for final velocity, right? So we can use this one. We can use this equation to solve our problem. So after we figure that out, everything becomes easy. So we can use this equation to solve the problem. Plug in all the numbers. Initial velocity is 0. 2 times 5 times 30.5. And if you use SI unit, you don't need to worry about a unit. So you can just do your calculation and put the unit SI unit back in the end. So solve this algebra. And you punch this into your calculator. It should give you 17.5 meter per second. Okay, pretty straightforward, right? So look what we did. We identified the three known quantities, and we identified the unknown quantity asked us to solve. And we find the equation that has those four variables. And then we use algebra to solve the unknown. Yeah, okay. B, how much time it has napped. So which one should we use? Which one should we use? So this one we know initial velocity. Check. Now we do know final velocity. Check. We know acceleration. Check. Ask for t. Which equation has those four variables? Looks like this one, right? We know initial velocity, we know acceleration, we don't know t, we know final velocity. We can use this one to solve the time. So using this one, and if you solve t in algebra, it should give us, plug in all the numbers, give us 3.5 seconds. And then it asks us to calculate the average velocity. First, we can at least use the definition of average velocity, right? Displacement over time, because we know displacement and we know time now. And then we also know initial velocity, final velocity. Okay, first calculate using the first method definition. Average velocity displacement over time. Displacement is 30.5 times 3.5 meter per second. Second method, we also know average velocity is initial velocity plus final velocity divided by 2, plugging all the numbers. That's the same thing. Okay. First example solved. Let's go to example 2, a car chase. We have a car traveling at constant speed, 24 meters per second. It passes a police car, or, well, a police anyway, hide, and the police car saw this speeder here, and the predicted stay here until after 1 second the car already traveled to this distance. And then the police car start with constant acceleration, 5 meters per second square. We want to figure out how long it takes for the trooper to catch this speeding car. So how does it work? If we analyze at t equal -1 second, both the police car and the speeder has set its position to be 0. And then the speeder is traveling in front of the police car. The police car is accelerating. At some point, police car catches the speeder, and they are at the same position. So we need to build an equation. The position of the speeder and the position of the police car. We build this equation and find out how long it takes that the position of the police car equals the position of the speeder. So we need to build an equation for the speeder. Let's see. Build an equation for the speeder. So let's start from here. How long this speeder travels? At t equals 0, what's the position of the X car? At t equals 0, what's the position of the car? Is constant velocity, right? Constant velocity and travel for 1 second. So what is this displacement? What's this displacement here? Constant velocity motion, as we said, for constant velocity motion, it should be its velocity times 1 second. So that's the position of the car at t equals 0 second. And it's still going constant velocity. So its position should be given by v times t. Well, of course, you can write 1/2 at squared, but for the car, for the car is 0, so this term internally is 0. So this is the position of the car as a function of time. And we need to do the same for the trooper, for the police trooper. Okay, v for the car is 24, so in 1 second it will move 24 meters, and this is 24 times t. And the position of the trooper, from t equals 0, this is 0, this is our 0. From t equals 0, it moves starting from t equals 0. So v0t for the trooper, and the initial velocity of the trooper is 0. So this term is 0. 1/2 at squared. The acceleration of the trooper is 5. 1/2 times 5 t squared, which is 2.5 t squared. Now we're looking for the time that the police car catch up with the speeder. So their position are the same. So we can add the t that we are looking for. The position of the car is the same as position of the trooper. So we can build the equation. At this time, position of car equals position of the trooper. Okay, so the equation gives us 24 plus 24 times t equals 1/2 times 5 times d squared. And then we just need to solve this equation. This is going to give us going to give a quadratic equation 2.5 t squared subtract 24 t subtract 24 equals 0. Now the cavity is here. We indeed need to solve a quadratic equation to find the t. So let's do that. Now we solve the quadratic equation and we find out the time is 6.976 meter per second. So we solved question A. And then question B. How fast the trooper is going at that time? This one would be pretty easy. So we have initial velocity of the trooper, which is 0, and then we know the time, which is roughly 1.7, and we know the acceleration is 5 meter per second square. So we can use the first kinematic equation, right? The first kinematic equation you need to refresh is this one. So we know initial velocity, we know a, we know t now. To solve the problem, v0 plus at 5 times 1.7 second, roughly, sorry, I think it is roughly 7 seconds rather than 1.7. It's roughly 7 seconds. The time is roughly 7 seconds. So it's roughly 35 meter. That's per second. 35 meter per second. That's how fast the trooper is going when the trooper catch up with the speeder. Now let's look at our next example. So a typical jet airplane will land at a speed of 160 miles per hour, and it will have an acceleration. So decrease the velocity by 10 miles per hour per second. So this we need to convert those two numbers to SI unit before we solve. Let's see how we should convert it. Initial velocity, we need to convert 160 miles per hour to meter per second, right? So how to do that? We multiply by 1. We multiply by 1. So we need to know, convert 1 miles per hour to meter per second. 1 mile per hour equals to so 160 mile per hour is roughly 71.5 meter per second. And then we need to find out what's the acceleration. They give us negative 10 mile per hour per second. We need to convert 10 miles per hour to meter per second to convert 10 miles per hour to meter per second. So we need to multiply what is 1 mile per hour equals to and the acceleration actually is 4.47 meter per second. Okay, now we're going to solve. First question, what's the total displacement of the aircraft between touchdown and the runway coming to rest? Question, the airplane travels at a constant speed for 1 second. So we need to find this segment and then break. So during this 1 second, the acceleration actually is 0 because constant speed. And then break. There is acceleration here, which is negative 4.47 now, we know. We know the initial velocity in SI unit is 71.5 meter per second. Come to a rest. So final velocity here is 0. So we know 3 quantities. Right now, we know 3 quantities. We know, well, this one is easy to calculate. Let's call this one delta x1. Delta x1 is initial velocity times this 1 second time interval gives 71.5 meter, right? Now we're looking for delta x2. So the total displacement here should be just delta x1 plus delta x2. How to find out that x2 is a constant acceleration motion? And we checked that we have now 3 quantities: initial velocity, final velocity, and acceleration. We're going to find the displacement. Which equation should we use? Initial velocity, acceleration, final velocity. We're looking for displacement. So we choose this equation to solve displacement, right? Choose this equation to solve displacement. So we have, using this one, we can also have displacement is final velocity subtract the initial velocity divided by 2a. Plugging all the numbers, it gives us delta x2 equals final velocity 0, initial velocity 71.5 square, 2 times acceleration, which is 4.47 meter. Plugging all the numbers into your calculator, we should find 572 meter. So what's the total displacement? The total displacement for the constant speed part, displacement for the constant acceleration part, everything together is roughly 644 meters. So this is at least the length of your runway for airplane to land safely on the runway. Thank you for your attention. Hopefully we know how to solve problem in one-dimensional motion now.